Next, I want to talk about how to convert a DFT into a DTFT. How to convert x of k, a finite number of samples, n samples, into a continuous waveform made up of an infinite number of samples. Okay, so just to put a few more symbols behind this, we know how to go from a DTFT to a DFT. We just sample it. We sample it every omega equals 2 pi over capital N times k for k equals 0, 1, 2, and all the way up to capital N minus 1. So as a picture of that, we have our DTFT here. In general, it's complex. I'm going to draw it as a real value. And you already know that if it's a real DTFT, it must mean there's some sort of underlying symmetry with our x of n. And in particular, that symmetry must be its periodic conjugate symmetric if our DTFT is purely real. So let's see our DTFT looks like. Looks like this when we draw it between 0 and 2 pi. Of course, it has to be symmetric around our pi. Its magnitude, or its real part, would be symmetric around pi. Its angle, or its imaginary part, would be antisymmetric around pi. And that's not hard, right? It's not hard to go from our DTFT to our DFT. All we do is we just simply sample it. We might sample it here and here and here, such that one more sample would take us right up to 2 pi. And let's see, here we've got 1, 2, 3, 4, 5, 6 samples. And if we have 6 samples of our DFT, that means our x of n must have also had exactly 6 samples. So easy to go from the DTFT to DFT, we just sample it. But the problem is if we want to go from the DFT to the DTFT, that's saying we want to go from our x of k, where k is 0, 1, 2, 3, 4, 5, 6 values, right, total. And so our x of k looks something like this. And our question is, we want to be able to exactly, not approximately, but exactly know that the DTFT from which this was taken to an infinite precision looks like that waveform. How the heck can we do this? Turns out that you already know how to do it. Because we already know how to convert x of n into capital X of e to the j omega, right? We're just saying we already know how to find the DTFT, and that's just that mathematical equation. And you already know how to do that. This is equal to the sum from n equals 0 to capital N minus 1 of our time domain waveform times e to the minus j omega n. But we also know one more fact. We know how to go from our DFT and inverse transform that exactly to our time domain waveform. And that's just called our inverse DFT. That's also just a math equation we know. If you recall, that's equal to the sum, now we're going to sum over k, of x of k times e to the j 2 pi k little n over big N. Now, if you think about this a little bit, our goal is to start off with our x of k and end up, which is discrete, and end up with our x of e to the j omega. But if we take its inverse DFT, then this whole thing is just our x of n. But we already know how to take the DTFT of x of n. And once you take its DTFT, you've got x of e to the j omega. You already know how to go from this discrete sampled waveform into this smooth continuous, infinitely sampled continuous frequency waveform, e to the j omega, continuous in omega, just by going through x of n as an intermediary. And you can do the math. You can, when you write it out, it looks like clearly a sort of a nasty twofold summation. You've got this inner summation over k, which is this one, our x of k, e to the j 2 pi kn over capital N. And now we've got our x of n. And then to do that, now we're going to take our DTFT, which is the sum over n equals 0 to capital N minus 1. Oh dear, I forgot a 1 over n. There's that 1 over capital N. This whole thing, which is times e to the minus j omega n. And then this whole thing is equal to x of e to the j omega. So this is how to go from our discrete frequency world into our continuous frequency world. And this is so significant because if you can do this with discrete frequency to continuous frequency, that means you can also do it from discrete time into continuous time. As long as you haven't aliased your signal, this is the Rosetta Stone equation that lets you go from the discrete world to the continuous world to an infinite number of decimal places of accuracy. This has huge impacts upon all kinds of areas of life. I mean, just as one example, if you have a discrete number of different cameras that you're videotaping an event, this same kind of concept will let you create a virtual camera that you can pan anywhere that you want in that space. This is an amazingly powerful concept. Mitra takes this and does a little bit more algebra to it and makes it a little bit more digested so it can be computed a little bit faster. But this is at the heart of it. This is at the heart of being able to go from discrete to continuous exactly.